Okay friends, so now we will learn about surface chemistry, right? And so this is actually one of my favorite topics to teach on. So I believe you will also enjoy it and I will also enjoy studying this, right? And okay, so first of all, this is a very important topic and so there are some terms related to it, right? So as in adsorption, which is the main thing that we'll study today, right? Okay, sorry for that. Yeah, adsorption and then absorption. So what is the difference between adsorption and absorption? Adsorption is the, you can say, is the temporary or permanent deposition. And okay, you see the deposition or accumulation, things like that. You can think of adsorption, like to get a, you can say a picture of it, accumulation. And then what is absorption? Absorption is actually the penetration. When the molecules penetrate into another molecule, it is called absorption. But when the molecules are deposited or accumulated on the surface of the other molecule, it's called absorption. Okay. And now, so what are these molecules? So there's one molecule and there's another molecule. So this molecule actually goes and gets, you can say, deposited on this, like this. So the one which goes and gets deposited is called the adsorbate, and the one on whom it's being deposited is called the adsorbent. Right? Done. And okay, so these was the difference between like adsorption and absorption, which you need to know. Other things are there, but yes, not that important. One more thing you should know is what is sorption. Sorption is, can be said as a phenomena in which both adsorption and absorption occur simultaneously. So it's actually, you can say, in between adsorption and absorption. So you can say like adsorption and absorption. Okay, both these things are occurring in a simultaneous fashion. Simul, right? And okay, so now we come to like desorption, right? Desorption. So what is desorption? Desorption is nothing but it is the reverse of adsorption, right? And okay, so now we'll look into some more concepts about adsorption itself, because adsorption is the main thing that we will study in surface chemistry. So we'll look into the thermodynamics of adsorption. Thermodynamics of adsorption. So adsorption, first of all, is a spontaneous process. Okay, so what is this? This is a spontaneous process. When I say spontaneous, it means that delta G is negative, right? It is an exothermic process. Exothermic process. So del H is also negative. Okay, so also the entropy is negative. So you can say, how can this possible? Like, how can entropy be negative? Okay, for the particular process of adsorption is negative, one when you consider the whole system, the surroundings also. So in that, you can actually get to see that the whole entropy is positive, but when adsorption is occurring with the adsorbent and the adsorbate, that is negative. And why is it negative actually? Just think, like there's a gas molecule which is getting adsorbed on a solid surface, and it is forming like one compound. So what happens, like del n, the number of compounds are decreasing, right? It's getting more ordered, it has to be negative, right? And now we will come into an important aspect, that is what are the some of the factors which affect adsorption. Okay, some factors which affect. So one is the surface area. Let's say one surface area. How does it affect? So larger the surface area of absorbent, greater is the amount of the substrate is absorbed. So adsorbent, if adsorbent is large, so the surface area of the absorbent is large, then more uh, of the adsorbate is a more adsorbate is absorbed, right? So more adsorption happens, right? And we also have, you can say like the like important aspect like related to surface area only is that your coarse particles possess much less surface area as compared to finely divided particles of the same mass. So what like coarse means, like coarse, okay, so coarse and we have finely divided. So because why? Because more the surface area, more the adsorption. Finely divided particles have more surface area than coarse particles, right? Also we have the concept of pressure and temperature. So how does pressure affect adsorption? Temperature. So pressure, what happens actually is adsorption increases with pressure increasing, right? And for temperature, it actually there are two different cases for chemisorption and physisorption, which we'll see later. But normally what happens is that adsorption, you can say, decreases with temperature increasing. So but we'll look into this like specific aspect of chemisorption and your physisorption, right? So let us now look into those aspects. Physisorption and chemisorption. So first of all, what is the nature of the, like you can say, bonds, or you know, nature of force which is actually binding them. So this is actually why weak van der Waals force. Okay, so actually this is the wrong way of writing van der Waal. Van der Waal. Uh, you write van der Waal with small v, small d, capital W. That's how van der Waal is written. Like weak van der Waal forces, and these have like bonds, strong bond forces. Okay, and because of it has strong bond forces, it is irreversible. And because this has weak van der Waal forces, this is reversible, right? And physics option is multi-layered. Okay, like your in BET, which we learn BET equation are famous. So in there it's multi-layered, but in chemis option, this is actually your monolayered, right? And how does it depend on temperature? So as I said before, this like if temperature increases over here, absorption decreases, as I said before. But in chemis option, there's a different thing. Like with an increase in temperature, what happens is adsorption first, so absorption is like A, first increases and then decreases. Okay, so there's a like different phenomena for chemisorption, right? And yeah, so these were like mainly of the things of physisorption, chemisorption, and we will now go into the different forms of our adsorption isotherm. Okay, so we have your Frenwick adsorption isotherm, Frenwick or Frenlich, some people say Frenlich, and he gave this equation for adsorption: x by m is equals to k p per 1 by n. So what is x? X is our mass of the gas absorbed, right? And like mass, like x is the mass of gas adsorbed on the mass m. So this is actually mass of adsorbate, and this is mass of gas which actually adsorbent. Hmm. And this is like equilibrium pressure, so you can know. And k and n over here, these are constants which depend on the nature of the adsorbate, right? And if you look over here, x by m, and you have p. Okay, so a graph like this comes, okay, for adsorption. So because I already told you, like the adsorption increases with pressure increasing, right? So but obviously, like a better graph if you want, let's just take the logarithm of the whole equation. Log x by m is equals to log of k plus 1 by n log of p. Right, so let us plot our equation. Log x by m on y-axis and log p on the x-axis. So this is like y, this is x, that means this has to be m, this has to be c, and we get a like line like this whose slope is 1 by n and the intercept is log k. Okay, so this was of, you can say, of the Frenwick, what Frenwick proposed. And obviously there were some difficulties with it, and so one of the main difficulties with this was that at higher pressure you can see it is showing some deviation or curvature. Okay, but so therefore Langmuir also came up with a better model. Actually Langmuir models is considered to be a better model than Frenwick, right? Langmuir. Okay, and so he made some assumptions first before which I should say so that you can understand. So you know, like there's an adsorbate and adsorbent. So he said the adsorbate, like one site, one site can adsorb one particle. Okay, and the species which are absorbed on like different sites, they do not interact with each other. Okay, and the heat of adsorption, like adsorbate getting absorbed on the one side, the heat of the adsorption, like the del H, is same for all the sites, right? And there's a dynamic equilibrium in play. Okay, and yeah, that's more or less of it. And the main thing that he said of how he derived the equation was he considered a thing called theta, which is a fraction of the total surface, fraction of surface covered, right? So how much is the uncovered part? 1 minus theta is the uncovered, uncovered, right? Therefore, you can say that the rate of desorption, what is desorption? Desorption is opposite of adsorption. Desorption happens from where? From the site that is uncovered, right? And this is equals to, this is proportional to theta, right? Because desorption has to occur from the side which is covered because it is getting desorbed. It is, so first it has to cover, then only it can get like uncovered, right? So it has to be proportional to theta. Therefore, we can say like if we introduce a proportionality constant, we can say RD is equals to K d theta. whereas kd is the rate constant for the desorption process. Okay, and therefore the rate of adsorption is proportional to 1 minus theta, right? That means Ra is equals to Ka 1 minus theta, and P. Why P is over here? Pressure. This is because adsorption depends on pressure, but desorption doesn't depend on pressure, because adsorption is when it's getting attached, so pressure is dependent, right? And I said there's a dynamic equilibrium in play, therefore the rate of desorption should be equal to the rate of adsorption, and here comes our main play. Okay, so what happens over here is that we just equate both sides. Kd theta is equals to Ka 1 minus theta p, and we finally get the theta value as Kp by 1 plus K. So this is the main your relation where K is equals to Ka by Kd. Okay, so this is the main formula for adsorption and desorption. Now, very important to note, another formula which is derived from here, which is very, very important as well, is, so we know that theta is x by m, right? Right? Theta is x by m, where x is the mass of gas as absorbed and m is the mass of the adsorbent, because theta is the fractional coverage, right? So if we just replace theta by x by m, and right, so theta, you can say like x by m equals to theta, and we just do some like manipulation over here and there, right? Like proportional to theta. Okay, so this is proportional to theta. Okay, this is proportional, not equal. We just introduce one more constant, which is like k prime. Okay, therefore we can say like x by m is equals to k dot, so let us say this is k prime, the new constant, dot k, which is the old, by 1 plus kp, right? So this gets multiplied, and k prime into k, let us call it like k1. Okay, and so now if we do some manipulation over here and there, what we'll get is p by x by m equals to 1 by k1 plus p by k1 by k. Okay, and this equation is very, very famous and very used also, because this is the form of y is equal to mx plus c, so we can plot some graphs and we can see some things happening over here, right? And we will have some numericals on these equations and other equations as well, but that will be in the next class. But I'll just, before ending this video, I'll just say you some more things, like okay, I didn't show you the graph, right, for how it's come. So theta p, okay, remember this equation, kp by 1 plus kp, the graph for this. So we actually have a graph like this. Here theta is equals to kp, here theta is equals to kp to the power 1 by n, here theta is equals to 1. Okay, done. So how does this come? Okay, simple. Over here what happens? In this place pressure is low. Pressure is low. Therefore, we can say like 1 is much more than kp. So you see like the denominator. So the theta is equal to kp. What happens over here when pressure is high? we can say 1 is very less than Kp. So what happens? Theta is equals to Kp by Kp, which is equals to 1. What happens in the middle when it's intermediate pressure? So then we have like Kp to the power 1 by n. So we can see the relation, right? When pressure is low, theta is dependent on the first order of pressure. When pressure is high, theta is dependent on the like zeroth order of pressure, and when pressure is intermediate, it is dependent on the 1 by nth order of pressure. Okay, so these were the main concepts, and adsorption is used in many ways, like right in catalysis, especially in the solid catalyst adsorbs the gaseous reactants on its surface, right? So adsorption has a lot of uses in softening hard water, in removing colored materials, right? In gas masks, where the adsorbents preferentially absorb poisonous gases and thus purify the air so that we can breathe properly, right? Okay, so this was it, and then in the next class we'll see some numericals of surface chemistry. Okay, because this video has been very long, but look at the concepts. We will use this simple concepts only for our video.